All right, in this video, we're going to talk about two main theorems when it comes to dividing polynomials. The first is the remainder theorem. This is kind of fun and a little shortcut into dividing polynomials and then what that actually means. So I'm going to kind of summarize this for us. If you divide a function by another function, and you get a remainder, then it just so happens that that remainder is the value for when you plug in x equals k. If that remainder is 0, then it means that x equals k is a 0 of that function. And if it's not 0, then it's a little bit of a shortcut for you. Instead of having to plug in that value all the way and cube and all of the things. So let's look at an example right here of what this means. Okay, so use the remainder theorem to evaluate this quartic function at x equals 2. Now, since x equals 2 is given to us, I'm going to use synthetic division because my 0, or my factor, I should say, that I'm kind of looking at is this right here. That's what I'm dividing. This is the piece that I'm dividing into here because I have x equals to 2. Okay, so let's plug this into synthetic division form. So I have 2. I'm checking I don't have any gaps. Okay. I pull this 6 down. I get 6 times 2 is 12. I get 11 times 2 is 22. When I do that subtraction, I get 7 times 2 is 14. 16 times 2 is 32. And so it doesn't look like I'm going to have a remainder of 0. It does look like I'm going to have 25 as my answer. Now, again, what does that mean? One, if I wanted to try to write this in factored form, I could say that this is equal to x minus 2 times 6x cubed plus 11x squared plus 17x plus 16, and then I have a remainder of 25. What the remainder theorem says is that also means that f of 2 must be 25. So if I were to try to plug in 2 and apply all of those orders of operations, in the end of it all, I'm going to get 25. If you look at it in factored form, think about why that has to be true. If I plug in x equals 2 here, well, then this whole thing ends up being 0, and I'm just left with 25. All right, this leads us into then the factor theorem where we're trying to solve for polynomials. And I've alluded to this a little bit, but this is where we have been heading. So the factor theorem says when you are dividing the 0 into the function, you're going to get a quotient. And if you get a remainder of 0, then you actually get the factored form of the polynomial, with that being the 0. Okay, let's look down here at this example. All right, show that x plus 2 is a factor of this cubic function, and then find the remaining factors. Use the factors to determine the 0 of the polynomial. Okay, so if x plus 2 is the factor, then I know that when I find the factors, that x plus 2 needs to be equal to 0, and I'm going to use synthetic division since that's a linear term. And so I'm going to use -2 in my synthetic division here. 1, -6, -1, and 30. Now remember, in order for this to be a factor, my end goal is that this is 0. So let's make sure that that checks out. All right, 1, -2, I get -8, and +16, 15, and then -30. Yay! Okay, so this cubic is then equal to x plus 2 times x squared minus 8x plus 15. And then I could write plus 0 if I want to, but I want you to see like, oh, look, we factored it. This is a factor of this cubic, and the quotient that's left over is this cubic, or this quadratic function. So then let's think, do I have two numbers that multiply to +15 and add to -8? Hopefully you see that's -3 and -5. And so I get x plus 2, x minus 3, x minus 5. That is my complete factorization of this polynomial. I also know, because that is complete factored form, that I can find the zeros by setting each and every one of those pieces equal to 0, just like we did back with quadratics. So I already know x equals -2 is 1 from the synthetic division and all of those things. X equals 3 is going to be 1, and x equals 5. All right, this is a cubic function that has a positive leading term, so I know that's my end behavior. I have these zeros. I'm not really worried about scale. And they are all linear terms, so I'm going to cross through my axes like that. And so that's what this polynomial would look like, more or less just a nice sketch of that polynomial.